Welcome to numerical ship and offshore hydrodynamics. Today is the lecture 56. Today we are going to discuss on ship hydroelasticity using semi-analytic method. So, till last class we discussed the hydroelasticity using a complicated bound integral equation method together with finite element. However, this is enough motivation, this method gives enough motivation when actually you are dealing with some initial judgment on the behavior of the ship. For example, at initial design level, suppose you want to find out what would be the bending moment is coming, what is the effect of the elasticity and how to compute the design load at basic initial level, like in the basic design stage. So, that time you really do not want to run a very complicated or very sophisticated some numerical tool. So, at that moment this semi-analytic method will help you a lot. Okay. So, this is the keyword that you have to use to get this lecture. Okay. Let us now jump into this semi-analytic method. Now, here to do this, what we are going to do is we are going to take a rectangular barge. Now, this also applies for a ship shaped body also, theory because it will be more complicated. So, but at the basic level, let us drop the forward speed as well as the ship shaped body. So, let us start with the rectangular barge. Now, why I am telling it is rectangular barge, the simplification is that the rectangular barge has a uniform beam, right. So, therefore, assuming this rectangular barge as a beam will be much easier compared to the other ship shaped body. Okay. So, here the idea is we are going to find out the pressure using impulse response based method. Now, we have already discussed about the impulse response based method initially. So, again we are using the same technique to find out the sectional force, and then we are going to use some modal superposition technique to find out the structural deflection, to convert the PD, that partial differential equation, into the ordinary differential equation, and then we are going to solve it. Now, let us see, although we can call it a semi analytic method, but still it involves lot of mathematics and lot of numerical technique also, some basic numerical techniques still it is required to solve this problem. Okay. Let us start. Now, here this is how we are going to discretize the barge. So, we are assuming again is a Euler beam and this is the governing differential equation. Now, here to solve this we use the deflection, the Wxt. Now, we have split into two parts. Now, one part is the time dependent, which is q and t here, and second part is the space dependent, which is called the Wnx, and we call them the mode shapes. Normally, popularly it is known as mode shape. Now, what is this mode shape? Now, if you do the vibration analysis, of course, you know what is mode shape, but now for the beginners, now let us see that how the structure can be bent if you apply some load on it. So, then structure can oscillate in this fashion, right, and also the structure can oscillate in this fashion as well, right, and also if you look at it, the structure can be oscillate in this fashion also. Now, structure can be oscillate in this way also. Now, this is something called the mode shapes, or the how a structure can oscillate or and can the deflection. Now, if you remember the rigid mode, then we know that we have some 6 degrees of freedom. The structure only can oscillate, let us say, in the surge mode or sway or heave, right, or in case of pitch, the roll and then yaw. Now, in case of a flexible structure, it can oscillate in infinite different way. So, this is the difference, major difference between the rigid body and the flexible body. Now, in rigid body we know very well it is finite number of modes it can oscillate, but in case of a flexible body it can oscillate infinite way. Now, it is good for us that though it can oscillate in infinite number of modes, however, only first few modes are actually making some impact. So, therefore, actually we can take, let us say, the first 4 modes as your as your mode shape, and you can ignore the remaining one, and you can say that okay, the impact of the other modes is not influential. So, I can go ahead with this 4 mode. Normally, not exactly not 4, it is better to take at least first 6 of the flexible modes. Apart from the first 6 rigid mode, it is better to take first 6 oscillatory mode. Okay. So, now what is going to use is like here we have this mode shape. Now, we have this equation. So, we know the equation of the Wnx. So, what we know as follows, that we know the how the structure can oscillate, or how I get the structural deflection along the horizontal axis. Now, this is the same thing also we know in case of rigid body also. There is not much difference in this idea, like in case of a rigid mode also we know that a structure can oscillate in 6 different way, right. We can assume the structure can oscillate in this way or this way or this way. So, we know that in which 6 way the structure can oscillate. Then what is unknown to us is that what is the amplitude of the oscillation, is it not? So, you see that here also in case of a rigid mode also we can use the same ideology or same kind of definition, that I know that how my body is going to oscillate, but I really do not know what is the amplitude of the oscillation. For example, for in case of a heave, I can simply take it is the mode shape Wnx, you can say simply 1. Why? Because it is a horizontal lines, right. And then if I understand that amplitude is the what is my amplitude of the heave, right. So, see, this is the idealization of how I can see the heave mode in terms of this Wnx into q and t, is it not? Similarly, the pitch also we can thinking of, okay, it is maybe that theta, so angle, so it can oscillate in some fashion, but I really do not know what is the amplitude of the angular deflection. So, similar way also in that case the Wnx in case of a in case of a pitch, we can see that we can write in case of a pitch, maybe it is here let us say it is minus, let us draw this diagram, it may be minus 1 here, it may be plus 1 here, and it may be 0 1. So, we can define this Wx which is minus 1, let us say x equal to minus L by 2, which is 0 equal to at x equal to 0, and it should be 1 at x equal to L by 2. Based on this condition I can construct the value of Wx, right. So, and then we can define my pitch is this Wx multiplied by this q and t, right. So, I just what would be the mode shape for the pitch mode, I will give that work to you. Okay. So, now let us see that how we can use this same technique for the flexible structure, right. Now, where let us say we are using this 4 mode, and then we are assuming that to be a free beam. So, therefore, the bending moment and the shear force at the corner is equals to 0. So, if this is the body, so at this point the shear force and bending moment is 0, and at this point also shear force and bending moment should be equal to 0. Now, if I apply this boundary condition, okay, so then we can actually find out what is the mode shapes, right. Now, anyways, now we know that what is the definition of modes, as I say that for example, for pitch or heave, I know what would be my mode shape. Similarly, for other flexible mode also we know what would be the mode shapes. Okay. Anyways, so now what we are going to do is we define my deflection, the total deflection, which is W x, is nothing but the mode shape multiplied by the amplitude. Okay. So, we substitute that here and then we integrate along L. So, then actually we can get this equation 2.4. Now, this is very standard way of approaching this problem, and if you have this basic structural dynamics, you know that this is how actually we can convert the partial differential equation into the ordinary differential equation. What we do is like we assume a particular mode which is W n. So, then I can write this expression, this W n, substitute this into this differential equation, and then what I do is I multiply the another arbitrary mode shape W m x, so that I multiply here, and then I use this boundary condition, and then I integrate from 0 to L. So, therefore, in the right hand side also in this equation, this right hand side also I multiply by any arbitrary mode W m x, and then actually I integrate it. In the left hand side also I substitute this in this equation, and then actually I multiply by this W m x throughout. I multiply this W m x throughout, and then I integrate it from 0 to L. So, this is the very standard idea how we apply over here to convert this equation into the ordinary differential equation. Now, here this is all about the structural part. However, that most important thing is how I can write here in the right hand side this f x t, and this f x t actually it is a combination of the radiation force and the exciting force. Now, here unlike the previous one, when I derived the finite element formulation, that restoring force actually we use as a external force and keep it as the right hand side, but in this formulation actually we are using it inside the stiffness matrix. That means, in this Kf actually we are writing the hydrostatic component. Okay. So, this is but it is not necessary, like you can still ignore it, and you can still write here as F static also, you can do that. So, it is not that strict restriction that you have to write everything in the stiffness matrix, that is in the Kf only, not necessary. That hydrostatic part actually you can incorporate in the right hand side, and you can treat it as a external force. Now, here the more important part is how actually I write this radiation force and the exciting force in semi-analytic measure. Now, here now think is for the radiation force actually this is not that complicated. It is very well defined, in fact, like we do not have to use much imagination to find out how I write that radiation component. Now, radiation component you know very well that when actually you oscillate the body, you are oscillating the still water, and then you can oscillate in all 6 mode for the rigid body, right. Remember that how we obtain the radiation force in case of a rigid body, we have a body in still water. So, of course, it is z equal to 0, and then we oscillate in 6 different way. We oscillate in heave, I mean which mode actually I am interested. So, we are interested in the heave and pitch. So, therefore, we oscillate in the heave mode, and then we sometimes we oscillate in the pitch direction also. But here when you have the infinite way, you can oscillate the body. So, therefore, this radiation should be combination of all this infinite mode, right. Now, if you remember again for the strip theory, when actually we try to figure out what is my radiation force, or you can write Fr, or let us say it is in the, let us say in third mode. So, then we have to add the radiation force, right, for the third mode when you oscillate the body in the third mode, plus radiation force in the third mode when I oscillate the body in the fifth mode, right. So, in that way we have this added mass A33, and then we had the added mass A35 and so on, right. So, similarly here also when you find out the radiation for the mth mode, then I can oscillate it on all nth mode, we can do the oscillation, right. So, therefore, that is how we can write this equation. Now, as you know, it is similar to your rigid body. In case of a rigid body, how we write this radiation force? If you remember this radiation force F of r, it is minus of added mass infinity, and let us say if you are trying to write in the third mode, then we write this into your x double dot 3, and it is 3, and then now let us ignore the all other modes, only writing for one single mode, then it is the plus or sorry or minus, it is 0 to infinity, it is k m n tau, which is the memory part of the solution, omega dot into x comma t minus tau into d tau. Now, this we know for in case of a x dot, this we know in case for a rigid body, right. However, in case for a the flexible body, you have infinite number of modes. So, therefore, it is very we have to understand that it is not that trivial, or not even the rigid body also not trivial. Here it is more complicated, that I am using some flexible mode, let us say my sixth or the first flexible mode, it is basically the seventh mode in general. If you consider first 6 as a rigid body mode, the 7 is the first flexible mode. Now, if you oscillate, so in seventh mode, how we oscillate the body? If you remember that my that picture, you actually oscillate the body like this way. Now, here when you oscillate the body like this way, then what would be the contribution like when this body is oscillating like this way? You see that difficulty, it is like here I even it is feeling even we have to have complicacy to feel that if I oscillate the body in heave mode, how I get the force at the pitch mode. Even in the rigid body, it is very difficult to realize. Now, in case of a flexibility, it is far more critical to realize that when a body is oscillating in this way, then what is the contribution when it oscillate in like this mode? I mean, what is the contribution in the force in that other mode? So, therefore, it to make it little bit simpler, what normally we assume that we here in case of a hydroelasticity, we use we do not consider the cross coupling thing. So that means we have the non-zero component when mn is not equal to 0, when m is equal to n, yeah, and when m is not equal to n, then this goes to 0. So, it is actually a simplification, and if you read the journal, in fact for the plate, there is a study that sometimes that this cross coupling added mass for the flexible body also have a big role. However, in our case is simplistic way, not simplistic, little simpler way, we assume that there is not much effect when actually m not equal to n. So, when m equal to n, we have only taken the contribution. So, here though I write it is in general the expression, this is a general expression. So, however, in practice we only apply this when m and n both the index are same. Okay. Anyways, so now here this is again the infinite frequency added mass, and this is how actually we can get the value for the memory part or the KMN. Okay. Now, here we do not have much time to discuss how we could get the this added mass and frequency domain added mass and damping value for the flexible structure. But at least for the barge there are some results available in literature, in the reference actually. When we discuss the reference, that time we discuss this the paper where actually you can at least get the added mass damping coefficient, the frequency domain added mass damping coefficient. Okay. But anyway, the idea is same, that in order to get the time domain this km and tau, you need to know the frequency domain added mass and frequency domain damping data for the flexible structure also. Let us see how I can incorporate this idea in this semi analytic method. Okay. Now, here I know this is my definition. So, in previous equation, this here I replace in this equation this expression, and once I replace this expression here, I know this is the my value, right. Because here this mn, as I said that it is only possible when m equal to n, though I mentioned this mn whatever. So, anyways, this if you multiply whole by this w n x, so finally you will get this expression, right. Because here this all these space terms will coming out of the integration sign. Now, just I will show you here this, if you do this, if you substitute here, so it is double derivative, right. So, if you do over here, this minus omega square will comes out, and then because this is not depending on the t, so it will remain as it is, and again if it is a vector, because it is a vector, so q n dot will be there and then w n x will be coming out. Okay. Now, here again I am using this x double dot equal to minus omega square into x. So, that is why I can write that x double dot equal to minus omega square, and this x actually w n x, it is nothing but my q n t into w n x. So, this w n x will comes out, and this part is entirely depending on the t, right. So, now as you know that initially I multiply everything with the w m x, which is the arbitrary mode shape. So, when you multiply this, then finally you have this expression 2.10, because here if you multiply the w m x. So, here I just have a w m x, and then we need to integrate from 0 to L. So, therefore, I integrate it from 0 to L, and therefore, I have this expression, right. This is very trivial. Just you just sit here, substitute here, and you can get this expression, right. Now, this is k dash is nothing but this expression which is the independent of the WMX. So, I just to make it little bit eye soothing, I just rewrite the whole expression. I simply replace by the k dash. K dash is nothing but the term which is inside the inside here, inside the square bracket in 2.9. Okay, fine. So, this formulation is not that, it is just you have to sit and replace the thing, you will get this expression 2.10 and 2.11. Now, this idea is actually a little bit complicated when you calculate the same thing for the exciting force. Now, if you remember what is the expression for the exciting force, or what is the physical phenomena that we are going to replicate for the exciting force. Now, you see that when you do the exciting force, you actually take the ship as it is and then you hit a waves and then you try to figure out what is the force, right. Now, the question is, in case of a rigid body, I understand it. Now, in case of a flexible body, then wave will hit in which type of or which position of the ship. For example, suppose I approximate the ship is like this and then I allow the wave is hit into this object. Are you getting my point? Now, this thing is, I understand that body does not move, right. However, the waves is coming and hitting to the object. Now, the question is that body does not move, but is a flexible body, then which mode I consider? Like, can I do this for all modes? Like, in case of when I try to figure out, let us say try to find out my exciting force and then for the mode let us take 7. So, at that time, do I consider that this is the fundamental structure and it will be stand still, and then I hit the wave here and try to figure out what is the pressure distribution along the hull, and then and then from this pressure distribution I can get the exciting force. When I doing it for the mode 8, finally the same thing, na, like in rigid body also, finally you have, if 6 degrees of freedom equation, you have 6 ordinary differential equation for each mode. So, here also we are having the if you take some 10 modes, you have 10 differential equation. If you take 100 modes, you have 100 differential equation. So, then now in case when you solve for mode 7, shall I take this body? When I say for the mode 8, shall I take this body? This is something actually confused us, and this course is all about discussing those part mainly, not the math part as such, because math part you sit and you can do that. I know that it is not that difficult. The difficult is the realization. Here the realization is that we do not really do this. We always take the body should be when it has rest at t equal to 0. We always take this body and then I allow the wave is hitting the body, and when actually I try to figure out the force, what I do is that what is the pressure field I am getting, I am integrating along the hull with the normal, and that particular time it should be now in case of a string, you know that all is in the vertical direction. So, that means it is the mode shapes are like this, something like this, the mode shapes are like this, are always is like this, something like this. So, therefore, it should be nz multiplied by this corresponding mode shape. Now, in case of a, let us say, first flexible mode, it should be Wx into ds. Now, this is the idea about the whole thing. Okay. Now, when we calculate the pressure, when we apply the boundary condition is always del phi del n del phi or whatever the mode, it is always diffraction mode is del phi 7, del phi 7 equal to minus del phi I by del n. This should be the always the boundary condition. It is a rigid body or flexible body, does not matter, this is the boundary condition. Now, apply this boundary condition when you get the force phi, and then from that when you get the pressure P, and then when you integrate the pressure P to get the force, that time only I multiply with the respective mode shape. So, this is the idea. Okay. Now, this is how I can get the pressure in frequency domain. This all actually we have to do all this exercise to get the data in frequency domain. Okay. So, now when you draw this data in frequency domain, see the way actually I replicate the radiation force in time domain. So, this is the expression I can get the radiation force in the time domain, where this FNT I can get again through the Fourier transformation, right. Because in Fourier transformation we have the all this frequency domain data, right. Now, time domain and frequency domain for the 0 speed, only the difference is the Fourier transformation. So, I have the frequency domain data, I do the Fourier transformation, then I can get the time domain data. So, this is how actually we can get the time dependent exciting force. Okay. So, today let us stop at this point. We discuss how we get the radiation force, how we get the exciting force. So, now therefore, I know how I get the total force over here, the total for Fxt. So, now in the next class I write this Fxt in the right hand side, I multiply by the Wmx, and then I will show you how semi analytic, how to use this the structural equation, that beam equation, Euler-Bernoulli beam equation, and how we are using some semi analytic technique to find out the deflection and the velocity of the each mode. That means, we are trying to figure out how I get this q and t, right, which is actually again it is in this equation. So, we are trying to figure out the q and t in the next class. So, now just to conclude, I have this expression Fxt in the right hand side, we know the mode shape in the left hand side. So, how I convert this into the ordinary differential equation for the time mode, and then how to solve this the ODE in T in analytic method. Okay. Thank you.